Hello everyone. So this is the lecture on the classroom questions of the chapter atoms and nuclei. So you can see the first question on the screen. A fossil bone has carbon 14 to carbon 12 ratio, which is given as 1 by 16 of that in a living animal bone. Now if the half-life time of carbon 14 is 5730 years, then what is the age of the fossil bone? So here in this question you see n by n naught value is given as 1 by 16. Now this can be written as 1 by 2 to the power 4. Okay, so what is the half-life time? 5730 years. Yes, so we have this relation n by n naught equal to half to the power t by t, and here you're finding out t, small t. Therefore what is the value of n by n naught? That is half to the power 4 equals to half to the power small t by 5730. Now since you have same basis on both sides, therefore you can write down 4 equals to t by 5730. So t equals to, you get 22920 years. Okay, option number C is the answer. Okay, so question number 2. Now which of the following is a possible nuclear reaction? Look, in these kind of questions you actually check the atomic number and mass number conservation. Like the mass number of the left side, when you add them up, they should match with the mass numbers on the right side. Same goes with atomic number. So if you check here, only option B will be valid. Here 23 plus 1 24, 20 plus 4 24, and here 11 plus 1 12, 10 plus 2 12. So your answer is option number B. Okay, next question. In the reaction this, like hydrogen 2 plus hydrogen 3 is giving you helium 4. Now here binding energies of hydrogen 2, 3 and helium 4 are given as A, B, C. Then which of the following option is correct? Now always remember, okay, first of all let's write down the equation giving you helium 4. Now the binding energies are given as A, B, C. Always remember, binding energy of daughter is always greater than parent, and mass of parent is always greater than daughter. Okay, we have another question related to mass. In the present question, since binding energy of daughter is greater than binding energy of parent, therefore energy released will be daughter binding energy minus parent binding energy. That is C minus A minus B, which is option number C. Next, number 4. So here the radius of aluminum is given 3.6 Fermi, aluminum 27, radius of tellurium 125 you have to find out. So you can do this in two methods. Okay, one method is like R equals to R naught A to the power 1 by 3, right? So say you are finding for tellurium, so that is the second case. Let's write R2, and we know value of R1 is 1.2 Fermi, right? And 125 is the mass number for tellurium to the power 1 by 3. So this gives you 1.2 into 125 is like 5 cube. Yes, so 5 cube, and you have 1 by 3, so this gets you 1.2 into 5. Yes, so there is 6 Fermi. This is one way of doing it. The other way is, we know R equal to R naught A to the power 1 by 3. So R2 by R1 equal to A2 by A1 to the power 1 by 3. And second case, 125 divided by first case, mass number is 27, 1 by 3, so which gets you 5 by 3. So R2 is 5 by 3 of R1, 5 by 3 of R1 value is 3.6. Therefore the result is 6 Fermi again. Okay, So next question, this is option number D. Number 5, which of the following cannot be emitted by a radioactive substance during the decay? You see, in a radioactive decay process, alpha comes out, right? Beta minus comes out, which means electron comes out. Beta plus comes out, which means positron comes out. Then you have, along with electron, antineutrino comes out. Along with positron, neutrino comes out. And gamma, photons also are released. Okay. So photons also are released. Therefore, here which of the following cannot be emitted? The question is cannot be emitted. Okay, so proton and electron, proton and neutron cannot be emitted. So out of the given options you have proton only, so you'll go with proton. Okay, so your answer is proton. Number A. Next, question number 6. If binding energy of hydrogen atom is given, the energy required to remove electron from first excited state of lithium plus. So firstly find out what is the energy at the first excited state of lithium plus 2 plus it is. Okay, so for hydrogen like systems, the energy relation was minus 13.6 z square by n square electron volt. So minus 13.6 into, for lithium z number is 3, and what is said here, first excited state, that means n value is 2. So this will give you minus 30.6. Okay, so energy required to remove the electron will be plus 30.6. Okay, and if you want to go by relation, actually you are knocking out the electron, right, from a particular orbit. You are knocking out totally, that means the electron is going to infinity. So energy required is E infinity minus E respective, here first excited state, that is E2. So it will be E infinity 0 minus 30.6. So your answer is plus 30.6. Option number A. Okay, option number A. Number 7. Binding energy per nucleon of H2, hydrogen 2 and helium 4 are given, 1.1 and 7. Mind it is binding energy per nucleon. So now 2 neutron combine to give you 1 helium nucleus. So your reaction will be, your equation will be He2 neutron, they combine to give you helium 4. 1.1 was the binding energy per nucleon. Therefore 1.1 into 2 will be the binding energies. Here 7 is the binding energy per nucleon, therefore 7 into 4 will be the binding energy. Now as we discussed this before, that binding energy of daughter is always greater, right? Therefore 7 into 4 daughter binding energy minus parent binding energy. Yes, 2 into 1.1 into 2. So this will get you 23.6. Okay, just check the calculation. So the answer is option number B. Next question, number 8. Now in Rutherford's alpha particle experiment with thin gold foil, 8100 scintillations per minute are observed at an angle of 60 degree. Number of scintillations per minute at an angle of 120 degree will be what? Now we talked about this relation, like this scintillation means sparks, and sparks happen when this alpha particle are captured by the detector in Rutherford's experiment. Okay, so there we talked about a relation. Number of alpha particle is inversely proportional to sine to the power 4 theta by 2. So here in the second case you are supposed to find out the value of n. So n2 by n1 is sine to the power 4 theta 1 by 2 sine to the power 4 theta 2 by 2. So sine to the power 4 theta 1 is 60, so sine to the power 4 60 by 2 is 30, and sine to the power 4 120 by 2 is 60. So the values are sine 30, what is the value? Sine 30 is half, right? Sine 30 is half to the power 4, and sine 60, what is the value? Root 3 by 2. So since it is in the denominator, we'll be writing 2 by root 3 to the power 4. So you get n2 is like 1 by 9 into n1 value is 8100, and that comes out to be 900. So your answer is option number A. Going to the next question. Radioactive nucleus having initial, well, this is mass number, okay, A, and initial mass number A and atomic number Z, emits 3 alpha and 2 positrons. Ratio of number of neutron to that of proton will be what in the daughter nucleus? So your equation is like ZXA is the nucleus. This is giving you Y, and along with that 3 alpha is released. So alpha is He24, right? And 2 positrons. Is the question saying positrons? Yes. Positron is +1 0. So here you see 4 3 12, 2 into 0 is 0. So the daughter should have A minus 12 number, A minus 12 mass number. Yes. And here in the atomic number, if you see 326 212, right? So 6 and 2 is 8. So the daughter will have Z minus 8 atomic number. Therefore n by Z. Now neutron number, how do you find out? Mass number minus atomic number. A minus 12 minus Z minus 8 divided by Z minus 8 is the proton number or atomic number of the daughter nucleus. So this gives you A minus Z minus 4 divided by Z minus 8, which is option number B. Okay, so question number 10, let's see. So you have this like energy levels A, B, C of a certain atom are given. Now EC is highest, followed by EV and followed by EA. These are the energies. Now lambda 1, lambda 2, lambda 3 are the wavelengths of radiation corresponding to transition from C to B, B to A and C to A. So which of the following relation is correct? So you can set up a diagram for that. Like A, B, C. C to B emitted is lambda 1, then B to A emitted is lambda 2, and C to A lambda 3. Now EC was the highest, followed by EB, followed by EA. So from here you see, you can clearly mark, or you can clearly notice that EC sorry, EC will be equal to EA plus EB. Now we can write down E equals to HC by lambda, right? So for EC it will be HC by lambda 3, HC by lambda 1, HC by lambda 2. So this is 1 by lambda 3, 1 by lambda 1 plus 1 by lambda 2 after cancelling all HC. So lambda 3 can be written as lambda 1 lambda 2 by lambda 1 plus lambda 2. So option number D is the answer. Okay, so question number 11 next. Ratio of minimum wavelength of Lyman and Balmer series. Okay, so what was the minimum wavelength of Lyman series? 912, right? 912 angstrom. Maximum was 1216, yes. And minimum for Balmer series was 3646 angstrom. Maximum was 6563. So if you take this ratio, 3646, you will get 0.25. Okay, option number B. An unstable heavy nucleus breaks into two nuclei which moves away with velocities in ratio 8:27. The ratio of the radii of the nuclei is what? So you see, the nucleus was at rest previously, of course, and it broke into A1, A2, and speed, like the ratio is 8/27, right? So V1 is 8, then V2 is 27. A is the parent nucleus and like mass number of the parent nucleus, and since it was at rest, so U is 0. Now by momentum conservation you can say that A, mass of each nucleus, speed of parent. This is momentum before collision. A1, mass of each nucleus, speed of the first, this nucleus. The second one, A2, Mn, V2. Now in radioactive process, parent is always at rest, right? Decay, in radioactive decay process, you have a nucleus and it keeps on emitting particles, so that parent nucleus remains at rest, therefore this is 0. So 0 A1 Mn V1 plus A2 Mn V2. So this Mn also can be cancelled, and by taking the magnitude you can write down A1 V1 equal to A2 V2. In fact it has to be A1 V1 equal to minus A2 V2, but we are considering the magnitude. Okay, so A1 by A2 is equal to V2 by V1, and that is 27 by 8. So that is your mass number ratio. Now what is the formula for radius? R0 e to the power 1 by 3. So R1 by R2 equal to A1 by A2 1 by 3. Yes, so that is 27 by 8 to the power 1 by 3, which gets you 3 by 2. Okay, so what is the answer? Answer is option number C, 3 by 2. Question number 13. For a radioactive material, half-life is given 10 minutes, and initially there are 600 number of nuclei. So disintegration of 450 nuclei will take what time? Okay, that means half-life is 10 minutes. So original 600, and what remains finally, you see, number of nuclei that remains will be 600 minus 450, which is 150. Now we know this relation n by n naught equal to half to the power t by t, right? So 150 by 600 equals to half to the power t by t by 10. So here you get like 154 times, so you can write down this. So time is 20 minutes. Okay, option number 1. Next question. Total energy of an electron in an atom in an orbit is this. The kinetic and potential energies are what? Now we know, you see, okay, doing it here. We know that kinetic energy is minus times of total energy, potential energy is double of total energy. Okay, so your answer will be 3.4 and minus 6.8. Okay, option number 3. Next, 15 number. alpha particle consists of, alpha particle has 2 proton and 2 neutron. Okay, alpha particle is helium nucleus. Next, 16 number, ratio of the mass density of nuclei of calcium 40 and oxygen 16 is close to what? Now we know it well that nuclear density is a constant quantity. Yes, so nuclear density is 2.3 into 10 to the power 17 kg per meter cube. This is constant. So ratio will be what? Like rho 1 by rho 2, that will be 1 only. Option number 1, answer. Question number 17. Now, radiation coming from transition 2 to 1 of hydrogen atom. Now this falls on helium plus in n equal to 1 and n equal to 2. Now when it falls, look, for 2 to 1 transition, hydrogen will release 10.2 electron volt of energy. Now if that 10.2 electron volt of energy falls on n equal to 1 and n equal to 2, you have to find out the electron in helium plus will jump to which n final number. Okay, so firstly, energy released from hydrogen transition is like E2 minus E1, which is minus 3.4 minus 13.6. Now this is like 10.2 electron volt. Okay. Now for helium plus, now you have to do some calculation. So for helium plus, En radiation is minus 13.6 Z square by n square electron volt. Yes. So E1 will get you minus 13.6 into 2 square by 1 square, that is minus 54.4 electron volt. E2 will get you minus 13.6. E2 is the first excited state, okay, into 2 square by 2 square. Now this is getting you minus 13.6 only electron volt. E3 will get you minus 13.6 into 3 square by 2 square. No, I made a mistake here. It should be Z square, 2 square by 3 square. So this will get you on calculation minus 6.04 electron volt, and E4 will get you minus 13.6 into 2 square by 4 square, minus 3.4 electron volt. Now you see, you have to check which of this energy level difference will get you 10.2. Okay, so it is pretty obvious that this 13.6 and 3.4, the difference will get you 10.2. Therefore E4 minus E2, E4 value is minus 3.4 minus 13.6. This gives you 10.2, right? So the transition is from 2 to 4. This will be the transition. Option number 2 is the answer. Okay. Option number 2 is the answer. Next, last question. The radioactive substance has half-life 60 minutes. After 3 hours, the fraction of substance that has to be decayed, okay, will be what? Okay. So firstly, the 60 minutes is like 1 hour. Yes. So half-life is 1 hour. Question number 18. Half-life is 1 hour, and given time is 3 hours. So we know n by n naught is half to the power t by t. So half to the power 3 by 1, which is 1 by 8. Yes, so 1 by 8 is what? 1 by 8 of n naught. You see, 1 by 8 remains. The question is asking about what portion will decay, and that also in percentage. Therefore, portion that will decay is like, if I write that as n prime, obviously 1 by 8 remains, means 7 by 8 will decay. Okay, and in percentage, 7 by 8 into 100% you can do, and that will get you 87.5%. Option number A is the answer. Okay, if needed I'll explain this any of the solutions in live classes also. So for now I'm closing. Thank you.